Hi, I'm Zongheng from UC Berkeley. I'm excited to talk about Balsa, learning a query optimizer without expert demonstrations. This is joint work with my amazing co-authors Wei-Lin, Frank, Gautam, Michael, and Yang. Query optimizers are essential for data systems. They translate a declarative query into a high-performance execution plan. It is critical for the overall system performance by picking out the join orders and the physical operators. It is also widely applicable and used by many kinds of data systems, including relational databases as well as data analytics systems. However, they take years to develop. Here are three examples. Sparse SQL initially shipped a heuristic-based optimizer, and only 3 years after its first release did it build a full-fledged cost-based optimizer. Similar story for CockroachDB, which actually published a blog post on the 9 months of intense effort to ship the first optimizer. If we look at newer data systems, they may have new computation models, new optimization objectives, or they may operate on entirely new engines. In such cases, there's likely no existing system or an expert to build off from. So the development cost is even higher. So we asked the question, do we have to keep paying this development cost over and over? Can we actually learn to optimize queries without learning from an expert optimizer? We answer this question affirmatively. We propose Balsa, a reinforcement learning approach to learn to optimize queries without learning from an expert. Balsa is conceptually simple. Given a target execution engine to optimize for and a training workload, which consists of a set of training queries and a dataset, Balsa learns to optimize by trial and error. We ask for a training query from the environment. The agent performs some actions to produce a plan. This plan is then executed by the engine, which will return a latency or a reward. Now, given this feedback, the agent can update its policy to become better and better in producing good plans. In our work, we show that without learning from an expert system, Balsa can actually outperform both open source and commercial optimizers that have undergone decades of development. Let's first look at how Balsa produces an execution plan. Central to planning is the use of a value network, which is a simple function that takes in a query and a partial plan and predicts its final latency. If we have a value network, we can then construct a plan for a query in a bottom-up fashion. And here's an example. Let's say we have 3 tables to join and we must decide the best first join to perform. What we can do is to enumerate a bunch of candidates for the first join by picking out 2 tables in a particular order and applying a join operator on top. Once we have the candidates, we can invoke the value network in order to get a bunch of value estimates. These value estimates tell us which first joins are more promising than others, which are more likely to lead to a final plan that runs faster. One analogy we can make here is that in a partial game state, the value of a game state is the predicted final win probability. In our setting of query optimization, the value of a partial plan is the predicted latency of the final plan. So once we have decided the best first join to perform, we can actually keep on going and to decide the best second join, best third join, and so forth. This algorithm is called value network guided tree search, and running it will lead us to a completed execution plan for this query. This algorithm is a recent machine learning advance proposed by AlphaGo, and it is actually used in a number of other problems involving sequential decision making. So we know how Balsa produces an execution plan. Next, we must execute it in order to get a reward. And here lies the key challenge. Since Balsa doesn't learn from an expert, it doesn't have any expert data. So it can quite easily run into bad plans, which can be very slow to execute, taking hours or even days. This is actually a unique property to query optimization, unlike other RL successes. In other RL successes such as games, If an agent makes some bad actions, they typically lead the game to end faster, potentially speeding up the learning. But in our setting, if a plan takes a long time to execute, we don't get a reward, so the learning may suffer. To illustrate this key challenge, here's a schematic plan space for a given query. Prior research has shown that most plans in the plan space are going to be expensive and slow. While good plans do exist, they are rare and pretty hard to find. So in other words, all plans for the same query produce the same correct output, but their runtimes may differ by orders of magnitude. What this means for the agent is that in the initial stages of learning, the agent is likely to make random actions or random plans. And these random plans can be very slow, potentially making learning infeasible. We solve this challenge by using a technique called sim-to-real learning. In a nutshell, instead of directly learning in this real execution environment, we first pre-train Balsa in a simulation environment. Now, the only difference here is that instead of executing plans, we use a very simple cost model to quickly estimate their costs. So in this fashion, even though the cost estimates are not the most accurate, they enable the agent to quickly learn to identify the most disastrous or high-cost plans. So that after simulation learning, when the agent proceeds to real execution learning, it has a much safer starting point than random initialization. For the simulator, it doesn't need to be state-of-the-art performance. It only needs to be good enough to avoid the most disastrous plans. We chose to use the C-out cost model. It simply sums up the estimated cardinalities of all operators on the plan and returns that as the cost. It has two advantages. First, C-out is generic or logical plan only. It makes no assumptions on the physical environment or the physical operators. Second, prior research has shown that it loosely correlates with execution speed. Other simulators are possible and can be plugged into Balsa. After simulation learning, we proceed to real execution learning. And in this stage, there are two ways to hit slow plans. First, the agent may pick and execute a suboptimal plan of a training query. We solve this problem using safe execution. If a plan is clearly suboptimal, meaning that the same training query has seen a better latency from prior iterations, we can safely time out the plan. But we need to return a reward for this plan. So we can simply set this latency, this unknown latency, to a large number. This will penalize the agent and discourage it from making the same mistake again. Second, the agent must explore by occasionally executing unfamiliar plans in order to avoid local minima. The traditional way to do exploration is to pick random actions to explore. And we know that random actions or random plans are going to be slow. Our solution is to do safe exploration, where the agent only explores probably good plans. Our insight is that we can ask for multiple plans from the tree search, not just the best plan. Because tree search is itself an optimization process, its outputs are likely to be probably good. And we found that exploring in this set of k-best plans is significantly better than exploring randomly. These techniques complete the Balsa architecture. As a bonus idea, we observed something quite intriguing during our experiments. If we train multiple agents independently on the same workload for the same engine, we found that their agent experiences can differ quite a lot. What this means is that some agents may prefer using a certain operator more than other operators. And this implies that the individual agents may have a biased view of the entire environment, even though they may do quite well on the workload. Our idea is to group all these experience buffers into a diversified merged experience buffer. We then perform offline training on top of this larger buffer to produce a diversified agent. This diversified agent can do much better on the training queries, much better than the individual agents. And this is not surprising because it has more access to more data. Interestingly, however, it also does much better on unseen test queries. These are queries that are never included in any of these buffers. So this technique improves the generalization ability of the agent significantly. For more details and numbers, please see our paper. Balsa is related to several state-of-the-art work in the area of machine learning for query optimization. Balsa is a learned optimizer like DQ and NEO, both of which learn from an expert optimizer in one way or another. Most fundamentally, Balsa removes the need to learn from expert optimizers for the first time, while being able to surpass expert-level performance. The optimizer assistant BAO learns to set the best optimization flags per query for an expert optimizer. The innovative engine SkinnerDB proposes intra-query learning, where during a query's execution, it explores and executes many join orders. In its current form, it is limited to picking left-deep join orders. In contrast to this work, Balsa learns to produce plans with physical operators assigned, as well as supporting Bushy join orders. How does Balsa perform against real systems? We first evaluate against PostgreSQL. On the y-axis, I'm going to show the workload speedup, where 1x means Postgres plans performance. So anything bigger than 1x means Balsa plans are faster. On the x-axis, we show 3 benchmarks, including the more challenging benchmark JOB. We see that Balsa can actually outperform the expert, Postgres in this case, on both training and unseen test queries. There are differences in the speedup numbers depending on the benchmark because the inherent room for optimization is different. We went one step further to evaluate Balsa against a commercial DBMS. And in this case, Balsa can also outperform the expert. And notice that quite interestingly, the speedup numbers here on this engine are higher than those on Postgres. This is because this engine exposes a smaller search space, non-bushy search space. So the agent can explore a smaller search space much more comprehensively. Training Balsa is also quite efficient. On the y-axis, we are going to show the normalized runtime compared to expert plans. So bigger than 1x means slower than expert plans, and smaller than 1x means Balsa plans are faster. Here are the learning curves for the 3 benchmarks. So we see that Balsa takes about 2 to 4 hours to reach 1x, the expert level performance, and then a few more hours to reach its peak performance. So training Balsa is reasonably efficient. Finally, we compare Balsa with NEO, a state-of-the-art approach in the literature. NEO learns from expert demonstrations, which mean 1 expert plan per training query in its pre-training. Interestingly, we found that Balsa and NEO can reach similar performance on training queries, but on the test set, there is a difference. Here we see that NEO can fail to generalize to unseen queries with unstable performance. Balsa, on the other hand, can generalize successfully. The reason is because Balsa uses simulation learning in its pre-training, which doesn't give us the best cost estimates, but it does give the agent a large amount of experiences, making it more robust. On the other hand, NEO in its pre-training learns from expert demonstrations, which mean 1 plan per training query, and they are limited in data quantity and variety, making it less robust in real execution. To summarize, we have presented Balsa, a reinforcement learning approach to learn to optimize without learning from expert optimizers. The key challenge we overcome in this work is to mitigate slow plans during learning. Our paper has more detailed ideas and evaluation, and we also open source Balsa on GitHub. It is our hope to enable researchers to reproduce and build on it, and for practitioners to find the best plans for their queries on their hardware. With that, thank you for your attention.